Hey, you all. Did you know that right now, in this very instant, there could be another version of you sitting in an identical room, wearing the same clothes, hearing this exact same sentence? But just a fraction of a second from now, your lives will diverge forever. One of you will keep listening. The other might pause the video, get up for a glass of water, and from that tiny decision, an entire new universe could spring into existence. Not as science fiction, not as wild speculation, but as a serious, mathematically consistent interpretation of quantum mechanics developed by one of the most brilliant physicists of the 20th century, Hugh Everett III. Today, we're diving deep into what might be the most mind-bending idea in all of physics, the many worlds interpretation of quantum mechanics, and with it, the real scientific possibility of parallel universes. And here's the twist. We're going to do it slowly, carefully, and clearly, so that even if you fall asleep halfway through, your subconscious just might absorb the logic, the evidence, and the sheer wonder of it all. Because the physics of parallel universes isn't magic. It's not mysticism. It's the natural consequence of taking the equations of quantum theory literally and refusing to add extra assumptions just to make reality feel more comfortable. So get cozy, dim the lights, maybe lie back. And let's begin, not with fantasy, but with a single, stubborn experimental fact that has haunted physicists for over 100 years. It all starts not in deep space or a particle collider, but in a classroom demonstration you may have seen, the double-slit experiment. Imagine a barrier with two narrow, parallel slits cut into it. Behind that barrier is a screen that lights up wherever something hits it, like photographic film or a modern detector panel. Now fire tiny particles, say electrons, one at a time toward the barrier. Common sense says, each electron is a little bullet. It goes through either the left slit or the right slit, and then hits the screen behind, leaving a single dot. Fire many electrons, and you'd expect to see two bright bands on the screen, piles of dots stacked behind each slit. But that's not what happens. Instead, after many electrons are fired one by one, a pattern emerges on the screen. A series of bright and dark stripes, what physicists call an interference pattern. That pattern is the hallmark of waves. Think of water waves passing through two openings in a sea wall. The ripples spread out, overlap, and where crest meets crest, they amplify bright stripe. Where crest meets trough, they cancel dark stripe. But electrons aren't waves, they're particles. We detect them as discrete, localized impacts, click, click, click individual dots. So how can single particles, sent one at a time, produce a wave-like interference pattern? As if each electron somehow went through both slits at once and interfered with itself. That's the central mystery, and it's not just electrons. The same thing happens with photons, particles of light, protons, neutrons, even large molecules like buckyballs made of 60 carbon atoms. The larger the object, the harder the experiment becomes, but the principle remains. Quantum objects behave like they're in multiple places at once until you look. Because here's the real kicker. If you place a detector at one of the slits, say, a device that beeps whenever an electron passes through the left slit, something astonishing happens. The interference pattern vanishes. Now you just get two clumps left and right like ordinary bullets. The mere act of measuring which slit the electron used destroys the wave-like behavior. It's as if the electron says, fine, you want a definite path, I'll give you one, but only if you force me to choose. For decades, physicists interpreted this with what's called the Copenhagen interpretation, named after Niels Bohr's Institute in Denmark. According to this view, a quantum system, like an electron heading toward the slits, doesn't have a definite position or path. Instead, it's described by a wave function, a mathematical object that encodes all the possible outcomes and their probabilities. The wave function evolves smoothly and deterministically, following an equation we'll talk about in a moment. But when a measurement is made, when a human or a machine observes the system, the wave function collapses, instantly, randomly, into one definite outcome. Before measurement, many possibilities. After measurement, one reality. That sounds neat until you ask, what counts as a measurement? Is it the detector at the slit, the photographic screen, The scientist's eyes, her brain. Where does the collapse happen? And how? The equations of quantum mechanics, which work spectacularly well for predicting experimental results, don't include any collapse. Collapse is something added to the theory like a patch to explain why we only ever see one outcome. Enter Hugh Everett. In 1957, at just 27 years old, Everett submitted his PhD thesis at Princeton. His advisor was John Archibald Wheeler, one of the giants of 20th century physics. Everett's idea was radical in its simplicity. What if the wave function never collapses? What if the equations, just as they are, without any extra rules, describe everything, including measuring devices and observers? What if all the possible outcomes predicted by the wave function actually occur, but in different, non-communicating branches of reality? That's the core of the many worlds interpretation. No collapse, no special role for observers, just the wave function, obeying its own natural law, evolving forever smoothly, splitting the universe into multiple threads, each realizing one possible outcome. When the electron reaches the double slits without a detector, its wave function goes through both slits, interferes, and produces the striped pattern. When a detector is present, the detector itself becomes entangled with the electron. One part of the wave function says electron went left and detector clicked. Another says electron went right and detector stayed silent. Both branches exist, but once they've split, they no longer interact. You, the observer, become part of one branch. You hear the click. You see the electron on the left. You have no awareness of the other branch, where a different version of you hears no click and sees the electron on the right. Crucially, this isn't science fiction speculation. It's a direct consequence of taking the Schrödinger equation, the fundamental law governing quantum systems, completely seriously. Let me spell that equation out in words, exactly as you'd speak it. No symbols, just plain English. The rate of change of the wave function with respect to time equals minus the square root of -1, multiplied by Planck's constant divided by 2 pi, all multiplied by the inverse of the mass of the particle, multiplied by the sum over each direction in space of the second derivative of the wave function with respect to that spatial direction, plus the potential energy at that point multiplied by the wave function, all divided by Planck's constant divided by 2 pi, again multiplied by the square root of -1. Yes, that's a mouthful, but here, the key point. This equation is deterministic and linear. Deterministic means, if you know the wave function at one time, the equation tells you exactly what it will be at any future time. No randomness, no jumps. Linear means, if you have two possible wave functions that each satisfy the equation, then any combination of them, say half of one plus half of the other, also satisfies the equation. That linearity is what allows superposition. The electron's wave function can be partly going through the left slit and partly through the right slit, and the equation happily describes that blended state. Now when a measurement happens, say, a photon hits a detector, the detector is made of atoms, electrons, all of which also obey the Schrödinger equation. So the total system, photon plus detector plus environment, evolves into a superposition. Photon reflected and detector registered reflection plus photon transmitted and detector registered transmission. There's no sudden break, no magical collapse. Just the smooth, inevitable unfolding of the wave function into a more complex structure, one with multiple, distinct, dynamically independent components. Physicists call this process decoherence. It explains why the different branches don't interfere with each other in everyday life. When a quantum system interacts with its environment, air molecules, photons, thermal radiation, the information about its state leaks out rapidly into countless degrees of freedom. That entanglement spreads so fast and so widely that revering it, bringing the branches back into phase, becomes effectively impossible. It's like dropping a drop of ink into a swimming pool. In principle, if you could reverse every molecular motion, you could gather the ink back into a drop, but in practice, never. Decoherence is the reason the world looks classical to us, even though underneath it's quantum all the way down. Let's make this concrete with a simple example: Schrödinger's cat. You've probably heard the paradox. A cat is sealed in a box with a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays and quantum mechanics says it has a 50% chance of decaying in 1 hour, the Geiger counter triggers the hammer, which breaks the vial, and the cat dies. If it doesn't decay, the cat lives. According to the Copenhagen interpretation, until you open the box, the atom is in a superposition of decayed and not decayed, and so the cat is in a superposition of dead and alive. Only when you look does the wave function collapse into one state. Everett says, no, the atom does enter a superposition, then it interacts with the Geiger counter. The Geiger counter enters a superposition, clicked and not clicked. Then the hammer released and held, the vial shattered and intact, the cat dead and alive. And finally, you, the observer, when you open the box, you become entangled. One version of you sees a dead cat and feels grief. Another version sees a living cat and feels relief. Both are real. Both are equally valid. Neither is more original than the other. The universe has branched. Now you might object, but I only experience one outcome. Yes, you do, because you are part of the physical system. Your memories, your thoughts, your sense of self, all are encoded in the state of your brain, which is made of particles obeying the Schrödinger equation. When the branching happens, your conscious experience follows one branch. You don't feel the split. You don't notice the other you. From your perspective, it looks random, 50-50 chance. But from the perspective of the entire wave function, what some call the multiverse, nothing is random. Everything that can happen does happen, just in different branches. This leads to a profound shift in how we think about probability. In classical physics, probability reflects ignorance. A coin is either heads or tails mid-flip. We just don't know which. In the many worlds view, probability is about self-location. After the coin flip, there are 2 copies of you, one seeing heads, one seeing tails. The question, what's the probability I see heads, becomes, what fraction of future versions of me see heads? And that fraction is given by the squared amplitude of the wave function component, what's called the Born rule. Let me explain the Born rule carefully, again in words. Suppose a quantum system is in a superposition of 2 possible outcomes. Say, outcome A and outcome B, the wave function assigns a complex number, an amplitude, to each outcome. The probability of finding yourself in the branch where outcome occurs is equal to the amplitude for a multiplied by its complex conjugate, which is the same as the square of the absolute value of the amplitude for A, similarly for B. And because the total probability must add to 100%, the sum of the squared amplitudes for all possible outcomes must equal 1. Now here's a subtle point. In the many worlds interpretation, all outcomes occur. So why do we observe probabilities matching the Born rule? Why don't we see rare events, like quantum tunneling through walls, more often? Why does a fair quantum coin feel fair? This is one of the deepest questions in the foundations of quantum mechanics, and it's still debated. Some physicists, like David Deutsch and David Wallace, argue that the Born rule can be derived from decision theory. If you're a rational agent who cares about the welfare of your future selves, you'll bet as if the probabilities were given by the squared amplitudes, even though all outcomes happen. Others propose modifications, like adding a tiny amount of randomness or invoking self-locating uncertainty in an infinite multiverse. But the core idea remains. The appearance of randomness emerges from the deterministic branching of the wave function, combined with the fact that you only experience one thread. Let's talk about scale, because this isn't just about electrons and cats. Every quantum event with more than one possible outcome leads to branching, and quantum events are happening everywhere all the time. A single atom in your body undergoes spontaneous emission. A photon from the sun scatters off a molecule in the atmosphere. An electron in a transistor tunnels through a barrier. Each of these processes, when amplified by decoherence, can lead to macroscopic differences. How many branches are there? Not a fixed number. The wave function doesn't split into discrete universes like tree branches snapping off. Instead, it's a continuous field that develops an ever-increasing number of effectively separate components, like a river delta spreading into countless distributaries. At any moment, the number of distinguishable branches depends on how much decoherence has occurred, how many degrees of freedom have become correlated with the quantum event. Some estimates are staggering. Consider just the photons hitting your eye every second, about 10 billion. Each photon's path, polarization, and detection is a quantum event. Multiply that by all the particles in your brain, your room, the Earth, and you're looking at an incomprehensibly vast number of new branches per second. But, and this is critical, most of these branches are nearly identical. The differences are microscopic, a single atom vibrating slightly differently. Only when a quantum event gets amplified, like triggering a neuron, or changing which sperm fertilizes an egg, do branches diverge in ways we'd call macroscopically different. That leads to another common misconception, that many worlds implies anything is possible. It doesn't. The wave function only explores possibilities allowed by the laws of physics. You won't find a branch where gravity repels or where 2 + 2 = 5. The Schrödinger equation is strict. Energy is conserved within each branch. Causality is preserved. The branches don't interact, so no traveling between them, no sending messages, no meeting your other selves. They're not far away in space. They're right here, but orthogonal in the abstract space of quantum states, like two radio stations broadcasting on different frequencies, occupying the same room but never interfering. Let's pause and clarify what a world actually is in this framework. It's not a separate spacetime. There's only one spacetime, the one described by general relativity. But the quantum state of that spacetime, and everything in it, has a structure with multiple quasi-classical components. Each component looks to its inhabitants like a single, definite universe obeying classical physics, because decoherence has suppressed quantum interference within that branch. So when we say parallel universes, we really mean parallel quasi-classical histories within a single quantum reality. This view actually resolves several long-standing puzzles in physics. Take the measurement problem, the question of why measurements have definite outcomes. In many worlds, there's no problem. Every outcome occurs just in different branches. The problem vanishes because we stop demanding a single outcome. It's like insisting a movie must have only one ending, when in fact a branching narrative can have many, each self-consistent. Another puzzle, quantum non-locality as revealed by Bell's theorem. Experiments show that entangled particles, say two electrons with opposite spin, exhibit correlations that can't be explained by any local hidden variables. If you measure one electron's spin here, you instantly know the other's spin, even if it's light years away. Einstein called this spooky action at a distance. But in many worlds, there's no spooky action. When the particles are created, their wave function is a superposition. Spin up here and spin down there plus spin down here and spin up there. When you measure yours, you split. One you sees up and knows the distant one is down. The other you sees down and knows the distant one is up. No signal is sent. No influence travels faster than light. The correlation was baked into the global wave function from the start. In fact, many worlds is fully compatible with Einstein's theory of relativity, because the branching isn't a physical process happening in spacetime. It's a feature of the quantum state of spacetime. There's no universal now. When the split occurs, different observers may describe the branching in different orders, but all agree on the final correlations. Relativity and quantum mechanics, which famously resist unification and other interpretations, fit together more naturally here. Now let's address a question I know some of you are thinking. If we can't interact with other branches, isn't this unscientific? Isn't it unfalsifiable? That's a fair concern. A good scientific theory should make testable predictions. But here's the thing. Many worlds does make predictions. It predicts exactly the same observable outcomes as standard quantum mechanics in all experiments where collapse is assumed. Where it differs is in its explanation, and in what it says happens beyond our branch. But there are potential ways to test the reality of the other branches indirectly. One idea comes from quantum computing. In a quantum computer, qubits exist in superpositions, and interference between computational paths is essential for speedup. If collapse were real, if only one path were ever real, it's hard to explain why algorithms like Shor's factoring algorithm work so efficiently. The many worlds view says, the computation is happening in parallel across branches, and interference between them yields the answer. While not direct proof, the success of quantum computing is consistent with and elegantly explained by the reality of multiple branches. Another line of evidence comes from cosmology. When we look at the cosmic microwave background, the afterglow of the Big Bang, we see tiny temperature fluctuations. These are believed to originate from quantum fluctuations in the very early universe, stretched to cosmic size by inflation. In the Copenhagen view, these fluctuations collapsed randomly during inflation. But who observed them? There were no observers. In many worlds, no collapse is needed. The wave function of the universe simply branched, and we happen to live in a branch where the fluctuations led to galaxies, stars, and us. It's a more coherent story for the universe as a whole. And there's ongoing research into gravitationally induced decoherence, the idea that gravity itself might play a role in making branches separate. Some theories, like Roger Penrose's objective collapse model, predict tiny deviations from standard quantum behavior for massive objects. Experiments with increasingly large molecules and optomechanical systems are testing these limits. If no deviation is found, even for objects approaching the Planck mass, that would support interpretations like many worlds that don't require collapse. Let's now walk through a real, historical experiment that only makes sense if the wave function doesn't collapse, the quantum eraser. This is where things get truly trippy. Imagine a double-slit setup, but now we add a way to mark which slit each photon passes through, say by placing quarter-wave plates over the slits that rotate the photon's polarization differently. Left slit gives horizontal polarization, right slit gives vertical. Now, when the photon hits the screen, we can, in principle, check its polarization and know which slit it used. And as expected, the interference pattern disappears. We get two clumps. But now, after the photon has passed the slits and before it hits the screen, we insert a polarizer at 45 degrees. This polarizer erases the which path information. A horizontally polarized photon has a 50% chance of passing through as 45-degree polarized. Same for vertical. Crucially, if a photon passes the eraser, we no longer know which slit it came from, even in principle. And here's the miracle. For the subset of photons that pass through the eraser, the interference pattern reappears. Not on the full screen, but when you correlate the detection events only with photons that made it through the eraser, you see stripes again. How does Copenhagen explain this? It says the act of erasing the which path information after the fact somehow undoes the collapse and restores the interference. But that implies retrocausality, future choices affecting past events, which is deeply troubling. Many worlds gives a cleaner account. When the photon passes the slits, the wave function splits. Left slit, horizontal polarization, and right slit, vertical polarization. When it hits the polarizer, each branch splits again. For the left branch, passes polarizer and blocked by polarizer. Same for the right. The passes components from left and right now have the same polarization, so they can interfere. The blocked components don't reach the screen. So the interference was always there, in the full wave function, but hidden in the correlations. The erasure isn't magical, it's just selecting a subset of the branches where interference is visible. This experiment has been performed, not just with light but with atoms, and the results match quantum predictions perfectly. And while Copenhagen can calculate the outcome, many worlds gives a causal, local, time-symmetric story. No collapse, no retrocausality, just unitary evolution. Let's go deeper into the math, again in words, so you understand why interference reappears. Suppose the wave function after the slits is amplitude 1 times the state photon through left slit with horizontal polarization, plus amplitude 1 times the state photon through right slit with vertical polarization. The screen detects position, but polarization is a separate property. The probability of hitting a point on the screen is the squared magnitude of the total amplitude at that point. Because the polarization states, horizontal and vertical, are orthogonal, they're perpendicular like x and y axes. Their cross terms vanish when you square the sum, so no interference. Now insert the 45-degree polarizer. Mathematically, it projects the polarization onto the 45-degree direction. The horizontal state becomes 1 over square root of 2 times the 45-degree state plus 1 over square root of 2 times the 135-degree state. Similarly, vertical becomes 1 over square root of 2 times the 45-degree state minus 1 over square root of 2 times the 135-degree state. So the 45-degree component of the wave function is 1 over square root of 2 times left slit plus 1 over square root of 2 times right slit, all multiplied by the 45-degree polarization state. Now the spatial parts, left and right, are coherently added with the same polarization. So when you compute the probability, the cross terms don't vanish. You get interference. The key is entanglement. Before the eraser, position and polarization are entangled. Knowing polarization tells you position. After the eraser, for the transmitted photons, that entanglement is broken, or rather, transferred to the blocked photons. The interference was always in the global state. We just need to look at the right subset. This reinforces a deep lesson. Quantum states describe knowledge of correlations, not absolute properties. There's no true path of the photon, only correlations between systems. And in many worlds, all those correlations exist across the multiverse. Now let's talk about time. In the Schrödinger equation, time is a parameter. It flows uniformly, and the wave function evolves forward. But what about the arrow of time? Why we remember the past but not the future? Many worlds offers a novel perspective. In a branching multiverse, entropy, the measure of disorder, can increase within each branch, even if the total wave function evolves reversibly. Why? Because when a branch splits, the individual branches become more specialized, more ordered in their local records, but the multiverse as a whole gains complexity. Your memory of the past is a record, a correlation between your brain state and earlier events. In your branch, that correlation exists. In other branches, different records exist. The reason you don't remember the future is that future branching hasn't happened yet from your perspective, but the branching is time-symmetric in the equations. Some physicists, like Sean Carroll, argue that the quantum arrow of time, the direction in which decoherence occurs, aligns with the thermodynamic arrow, and both may stem from the low-entropy initial conditions of the Big Bang. Which brings us to cosmology and the quantum origin of the universe. In the 1980s, James Hartle and Stephen Hawking proposed the no-boundary wave function, a proposal for the quantum state of the entire cosmos. It describes the universe not as having a singular beginning, but as a smooth, four-dimensional shape, like the surface of a sphere, but in space-time, without edges. In this view, the Big Bang isn't a point of infinite density, but a region where time becomes space-like. In many worlds, this wave function doesn't collapse. It just is a vast superposition of possible cosmic histories. Some branches have inflation, some don't. Some have galaxies, some are empty. Some have life, most don't. We find ourselves in a branch compatible with our existence, not because of chance, but because only in such branches can observers arise to ask the question. This is the self-sampling assumption, a key part of the anthropic principle. But many worlds strengthens the anthropic principle. It's not that our universe is fine-tuned. It's that among the vast multiverse, some branches have the right constants for life, and we're in one. No designer needed, just the wave function exploring all possibilities allowed by physics. Let's clarify what all possibilities means. The wave function is constrained by symmetries and conservation laws. For example, electric charge is conserved in each branch. So you won't find a branch where an electron turns into a proton. That would violate charge conservation. The Hamiltonian, the operator that generates time evolution, encodes these laws. So the branching is lawful, not lawless. Now, a question I've seen often. Does many worlds violate Occam's razor, the principle that simpler explanations are better? After all, it posits countless unseen worlds. But Occam's razor favors theories with fewer assumptions, not fewer entities. Copenhagen adds an extra postulate, the collapse, and leaves it undefined. Many worlds uses only the Schrödinger equation and the standard quantum formalism. No collapse, no observers, no classical quantum divide. In that sense, it's simpler. As Einstein said, everything should be made as simple as possible, but not simpler. Many worlds refuses to oversimplify quantum reality. Let's compare it to other interpretations briefly, not to dismiss them, but to show why many worlds stands out. There's Bohmian mechanics, or pilot wave theory, where particles have definite positions guided by a wave function. It's deterministic and avoids collapse, but it's non-local. The guidance equation depends on the configuration of all particles instantly, violating relativistic causality. It also treats position as special, with no clear extension to quantum field theory. There's objective collapse theories like GRW or Penrose's model, where the wave function spontaneously collapses at random intervals, more likely for larger systems. These are testable, and experiments are closing in on their parameter space. But so far, no evidence for collapse has been found, and they introduce new constants and mechanisms not in the original theory. There's quantum Bayesianism, or QBism, which treats quantum states as beliefs, degrees of confidence an agent has about future experiences. It dissolves the measurement problem by making everything subjective. But many physicists find it unsatisfying for cosmology. What were the beliefs of the universe before observers? Many worlds, by contrast, is realist. The wave function is real and objective. It doesn't depend on observers. It's local in configuration space and compatible with relativity. And it's minimal, just unitary evolution. That said, it has its own challenges. The preferred basis problem. Why do we split into branches of dead cat and a live cat and not some weird quantum mixture? The answer is decoherence. Interaction with the environment selects a basis, called the pointer basis, in which states are stable and don't rapidly re-entangle. For macroscopic objects, that basis is almost always position or energy, classical-looking variables. Then there's the probability problem we touched on earlier. If all outcomes happen, why do we observe frequencies matching the Born rule? One promising approach is invariance, a symmetry discovered by Wojciech. Suppose two systems are entangled in a perfectly symmetric way. System A in state up correlated with system B in state up, plus a down correlated with B down. If you swap A's states and simultaneously swap B's, the total state is unchanged. Jerk shows that this symmetry implies the probabilities must be equal, 50-50. Extending this, he derives the Born rule from entanglement symmetries. It's not universally accepted, but it's a serious physics-based derivation, not an added postulate. Let's do a thought experiment to feel the reality of branching. Imagine you're about to perform a quantum coin flip, a single photon hitting a 50-50 beam splitter. If it reflects, you win $10. If it transmits, you lose 10. You've agreed to play. The photon is emitted. It hits the splitter. The wave function becomes square root of 1/2 times photon reflected and you happy, and $10 richer plus square root of 1/2 times photon transmitted, and you disappointed and $10 poorer. From outside, the state is a superposition. But from inside, as the you in the first branch, you only experience winning. You feel joy, you update your memory, you tell your friend, I won. Meanwhile, in the other branch, another you feels loss updates his memory and says, "I lost." Neither is wrong, both are real. Now suppose you play twice. 4 branches, win-win, win-lose, lose-win, lose-lose, each with amplitude 1/2 times 1/2, so squared amplitude 1/4. You before the flips know that after 2 rounds there will be 4 copies of you. One has $20, one has 0 twice, one has -20. The measure, the weight, of branches where you're ahead is 50%. So rationally, you should be willing to pay up to $10 to play once, because the expected utility, averaged over your future selves, is 0. This is how probability emerges, not from randomness, but from the geometry of the wave function. The squared amplitude acts like a measure on the multiverse, telling you how much reality fluid flows into each branch. You care about branches in proportion to their measure. Some worry this makes morality strange. If every choice is realized, does responsibility vanish? But no, you only experience one path. The you who chooses kindness creates a branch where kindness ripples outward. The you who chooses cruelty creates a branch of suffering. Both exist, but you, right now, deciding what to do next will become one of them. So your choices still matter profoundly. In fact, many worlds heightens responsibility. Every decision spawns worlds where its consequences unfold. Let's return to the double slit, but now with you as the detector. Suppose you stand at the left slit, eyes closed, and a friend flips a quantum coin. If heads, she opens your eyes just as the electron passes. If tails, she leaves them closed. If your eyes are open, you see which slit. If closed, you don't. Before the flip, the state is coin in superposition, you with eyes closed, electron approaching. After the flip, an electron passage. Coin heads, you open eyes, electron left, you see left. Coin heads, you open eyes, electron right, you see right. Coin tails, you keep eyes closed, electron in superposition, interference occurs. But now you are entangled with the coin and the electron. When you later learn the coin result, you split again. If the coin was tails, you see interference, because your memory has no which path information. If heads, you see clumps, because your memory does. The point, consciousness isn't causing collapse. Your brain is a physical system, subject to the same rules. Observation is just entanglement via interaction. Photons hitting your retina, triggering neural cascades, correlating your brain state with the external world. This demystifies the role of the observer. Physics doesn't need minds to make reality definite. Reality is definite, locally, in each branch, because decoherence makes superpositions effectively irreversible. Now let's address scale again with numbers, not to overwhelm but to awe. The number of decoherence events per second in a cubic centimeter of air at room temperature, roughly 10 to the power of 30. Each event can, in principle, lead to branching, but most branches differ only in microscopic details, like the exact position of a nitrogen molecule. How many macroscopically distinct branches are there? That depends on what counts as macroscopically distinct. If we define it as differing in the state of at least one neuron, then consider, your brain has about 86 billion neurons. Each neuron fires or doesn't in a given millisecond, roughly a binary choice. So the number of possible brain states is 2 raised to the power of 86 billion, a number with about 26 billion digits. That's the number of possible mental states. But not all are realized, only those connected by physical dynamics. Still, the multiverse is vast beyond imagination. Yet it's not infinite. At any finite time, the Hilbert space, the abstract space of quantum states, has finite dimension for a finite universe. Only in the limit of infinite space or time does it become infinite. And here's a comforting thought. In the multiverse, every possible good outcome that physics allows does happen. There's a branch where you aced that exam, a branch where you said the right thing, a branch where the treatment worked, a branch where peace was chosen, not as wishful thinking but as consequence. The wave function explores all consistent histories. Suffering exists in many branches, but so does joy, courage, love, discovery. The multiverse isn't dystopian, it's complete. But, and this is crucial, it doesn't absolve us of effort. You are here in this branch. The version of you reading this now, your choices, your actions, your kindness, shape this world line. Other branches are real, but they're not yours to change. Your responsibility is to this thread of experience. Let's shift to quantum field theory, the framework that combines quantum mechanics and special relativity and underlies the standard model of particle physics. In quantum field theory, the fundamental objects aren't particles but fields, one for each type of particle: electron field, photon field, quark fields, etc. These fields exist everywhere in space, and particles are excitations of the fields, like ripples on a pond. The wave function becomes a wave functional, a function not of particle positions, but of field configurations. The Schrödinger equation generalizes. The rate of change of the wave functional equals minus I times the Hamiltonian operator acting on the wave functional. In many worlds, the universal wave functional evolves unitarily, branching as quantum fluctuations in the fields decohere. During cosmic inflation, microscopic quantum fluctuations in the inflated field became the seeds of galaxies, each fluctuation pattern realized in some branch. And in quantum gravity, where we try to merge quantum mechanics with general relativity, the wave function may depend on the geometry of spacetime itself. The Wheeler-DeWitt equation, a candidate for quantum gravity, famously lacks a time parameter. Time emerges from correlations within the wave function. In many worlds, this timeless wave function still branches into different spacetime geometries, different matter configurations. Our experience of time is a feature of our branch. I want to emphasize, many worlds isn't about believing in parallel universes. It's about taking the math seriously. The equations work. They predict experiments with stunning accuracy. If you strip away the extra baggage of collapse, what's left is a single, elegant, deterministic evolution, and a multiverse as its natural consequence. Even skeptics admit its virtues. Steven Weinberg, Nobel laureate, wrote, "The trouble with quantum mechanics is not that it's strange, but that it's not strange enough. The many worlds interpretation embraces the strangeness, and in doing so, restores clarity." Let's recap the evidence for the reality of the wave function's full structure. 1. Interference in the double slit, even for large molecules, shows superposition is real. 2. Entanglement and Bell tests rule out local hidden variables, supporting a global, non-separable state. 3. Quantum eraser experiments show that collapse isn't irreversible. It's about information and correlation. 4. Decoherence explains the appearance of classicality without collapse. 5. Quantum computing relies on parallel processing across superpositions. 6. Cosmology needs a quantum description of the whole universe, where external observers don't exist. None of this proves many worlds, but it shows that alternatives require more assumptions, more mystery. Many worlds is the interpretation that adds the least. And now, as you listen, maybe drifting towards sleep, let this settle in. The universe isn't small, it isn't lonely, it isn't random. It's a vast, intricate, ever-branching tapestry of possibility, woven by a single, beautiful equation. You are here in this moment not by accident, but as one thread in a cosmic story too grand to tell in a single line. Let's begin with a question that haunts many who first encounter many worlds. If there are countless versions of me, which one is the real me? The answer may unsettle you at first, then liberate you. There is no single real you. There never was. What you call yourself is not a static object, but a process, a continuous thread of memory, perception, and causal connection winding through the multiverse. Before a quantum event branches the wave function, there is one stream of experience. Afterward, there are two, or more, each inheriting the full history up to the split, then diverging. Neither is a copy, neither is a shadow. Both are equally you at the moment of branching, just as the Mississippi River, after splitting at a delta, flows in two channels, both carrying water from the same source. This challenges our deepest intuitions about identity, intuitions forged in a classical world where objects have definite trajectories. But quantum mechanics reveals a deeper truth. You are not a point particle moving through time. You are a pattern, a stable, self-reinforcing structure in the quantum field, propagating forward, occasionally bifurcating when decoherence makes alternatives dynamically independent. Your sense of continuity comes from the fact that, within each branch, memories are consistent. The you who sees the electron go left remembers always having seen it go left, even though, a nanosecond earlier, there existed a superposition where both possibilities were equally real. This leads us to the concept of personal identity over time. Philosophers like Derek Parfit have argued that identity isn't about numerical sameness, being the exact same atoms, but about psychological continuity and connectedness. In many worlds, that view finds unexpected support. After a branching event, each successor has unbroken psychological continuity with the pre-branch you. Each has your memories, your values, your unfinished thoughts. So rather than asking which one is me, the better question is, what does it mean to care about my future selves? And the answer, as we touched on earlier, is that rational concern should be proportional to the measure of the branch, the squared amplitude, because that determines how much of the future you space a given outcome occupies. Imagine you're scheduled for a medical procedure with a 10% quantum risk of catastrophic failure, say, a nanobot swarm misfires due to a tunneling event. In 90% of the branches, you recover fully. In 10%, you do not. From the global perspective, both outcomes happen, but you, right now, facing the decision, should you undergo the procedure? A many worlds aware agent would calculate expected utility not as will I survive, because you will in most branches, but as what is the welfare of my future selves, weighted by their measure. If the procedure offers great benefits, say, curing a degenerative disease, the rational choice may still be yes, even knowing that in some branches, a version of you suffers, because the aggregate well-being across your future selves is higher. This reframes ethics. It doesn't erase responsibility, it expands it. Every action you take doesn't just affect this world, it seeds a family of worlds. A kind word may tip a conversation in one branch toward reconciliation, while in another, silence leads to estrangement. Both are real, but you, in this moment, choosing to speak, that choice determines which branch you will experience. And since you cannot know in advance which one that will be, only the probabilities, you act as if you care about all your future selves. That is the foundation of rational decision-making in a branching universe. Now let's shift to time, not as a river flowing in one direction, but as a landscape we move through. In classical physics, time is absolute. A universal clock ticks the same for everyone. In relativity, time is relative. Your speed and gravity affect how fast your clock runs compared to others. But in quantum mechanics, especially in many worlds, time takes on a subtler role. Recall the Schrödinger equation. The rate of change of the wave function with respect to time equals minus the square root of -1, multiplied by Planck's constant divided by 2 pi, all multiplied by the Hamiltonian operator acting on the wave function, all divided by Planck's constant divided by 2 pi, again multiplied by the square root of -1. This equation treats time as an external parameter, not as a quantum observable. But when we include gravity, as in attempts to quantize general relativity, time often disappears from the fundamental equations. The Wheeler-DeWitt equation, the cornerstone of canonical quantum gravity, has no time variable at all. It states, the Hamiltonian constraint operator acting on the wave function of the universe equals 0. In words, the total energy, including gravitational energy, of the entire cosmos is exactly 0, and the wave function is static. Time doesn't flow, it emerges from correlations within the wave function. For example, the position of a clock hand becomes correlated with the position of planets, the decay of atoms, the firing of neurons, And that network of correlations is what we experience as time passing. In many worlds, this static universal wave function still contains branching structure. Think of it like a frozen block of ice with dendritic cracks spreading through it, not in time, but in the abstract space of configurations. Each crack is a decoherent history. Our experience of now, moving forward, is like a drop of water tracing one path through the ice. We only see the local structure, not the whole. This resolves the so-called problem of time in quantum gravity. If the fundamental description is timeless, how do we recover dynamics? The answer is relationalism. Time isn't fundamental, change is. What matters is how one part of the universe changes relative to another. Your heartbeat relative to the sun's position. The expansion of space relative to atomic vibrations. In each branch, these relative changes proceed smoothly, giving rise to the illusion of a flowing time, even though the multiverse as a whole is unchanging. And here's a profound implication. The arrow of time, why we remember the past but not the future, may be a branching effect. In the early universe, the wave function was in an extremely low entropy, highly symmetric state. As it evolved, decoherence caused it to branch into a tree of increasingly diverse, higher entropy histories. In each branch, entropy increases away from the trunk, the Big Bang, because that's the direction in which records form, correlations that allow systems to encode information about earlier states. You remember yesterday because your brain state today is correlated with yesterday's events, via photons that entered your eyes, neural pathways strengthened by experience. In the opposite direction, toward what we call the future, those correlations haven't formed yet. So the psychological arrow, the thermodynamic arrow, and the quantum branching arrow all point the same way, away from the low entropy origin. Now let's consider whether time travel is possible in a many-worlds universe. In general relativity, certain spacetime geometries, like rotating black holes or wormholes, allow for closed time-like curves, paths that loop back to an earlier point in spacetime. This raises paradoxes. What if you go back and prevent your own birth? Many Worlds offers a resolution. You can't change your own past, but you can branch into a new timeline where the past is different. Suppose you build a time machine. You step in, set the dial for 20 years ago and activate it. What happens? The wave function evolves into a superposition. One component where the machine fails, another where it succeeds, and in that component, you arrive in a branch that diverged at the moment of your arrival. In that new branch, history unfolds differently. Perhaps your younger self meets you and that meeting alters their choices. But your original branch, where you grew up without meeting your future self, still exists untouched. You haven't erased it, you've spawned a sibling history. This avoids paradoxes. There's no contradiction in you being born in branch A, then traveling to the past of branch B, where a different sequence leads to a different version of you, or none at all. The Novikov self-consistency principle, which says only self-consistent loops are allowed, isn't needed. Inconsistency is resolved by branching. Experimental evidence. None yet. Time machines remain speculative, but the math is consistent. In 1991, David Deutsch showed that quantum computation in the presence of closed time-like curves doesn't lead to paradoxes if the many worlds view is adopted. The computation simply explores multiple self-consistent histories in parallel. Let's now turn to quantum immortality, a thought experiment that's often misunderstood, sometimes sensationalized, but worth examining with care. Imagine a quantum suicide setup. You sit with a gun pointed at your head, triggered by a quantum event, say, the decay of a single atom in 1 second. If it decays, the gun fires. If not, it clicks harmlessly. You repeat the experiment every second. According to the Born rule, after 10 seconds, the probability that you're still alive is 1/2 to the 10th power, about 1 in 1,000. But here's the twist. From your subjective perspective, you only experience the branches where you survive. In all branches where the gun fires, your stream of consciousness ends. So after 10 seconds, if you're still conscious, you know you're in one of the rare surviving branches. After 20 seconds, it's 1 in a million, but you are still there thinking, how unlikely. And in principle, you could keep going, experiencing an arbitrarily long sequence of miraculous survivals. Does this prove immortality? No, it proves subjective continuity, but only until all branches where you survive are exhausted. For any finite lifespan, there are branches where you live longer than average, but not infinitely. Eventually, biological decay, heat death, or quantum tunneling of your brain atoms will end all conscious branches. Quantum immortality doesn't grant eternal life. It just means your first-person perspective can't witness its own termination. Death is real for most versions of you, but the one asking, "Am I still here?" will always, by definition, answer yes, until the moment they don't. This isn't a reason to take risks, because while you may subjectively survive improbable dangers, the measure of surviving branches becomes vanishingly small. The vast majority of your future selves suffer or die. Rational action still minimizes expected harm across all branches. Now let's talk about the largest scales, the fate of the multiverse. Current cosmology suggests our universe is expanding at an accelerating rate, driven by dark energy. If this continues, we face the heat death. All stars burn out, black holes evaporate via Hawking radiation, and the cosmos approaches absolute zero, a uniform, featureless void. But in many worlds, even this isn't the end. Quantum fluctuations, tiny random deviations allowed by the uncertainty principle, can, over immense timescales, give rise to new structures. In an eternally inflating multiverse, some branches may undergo false vacuum decay. A bubble of lower energy spacetime nucleates and expands at nearly light speed, rewriting the laws of physics within it. Inside such a bubble, new constants, new particles, new possibilities emerge. Our universe may be one such bubble, born from a decay event in apparent vacuum. And within our vacuum, Poincaré recurrence suggests that, given enough time, far longer than the current age of the universe, random fluctuations could reassemble you, atom for atom, with all your memories intact. Not a copy, not a simulation, a reincarnation via quantum chance. In an infinite multiverse with infinite time, every finite configuration repeats infinitely often. But caution, this requires the universe to be finite in degrees of freedom, which it may not be. If space is infinite, or if quantum gravity introduces fundamental discreteness, recurrence may not hold. Still, the point stands. In many worlds, extinction is not erasure. Even when a branch fades into darkness, its information isn't lost. It's encoded in the global wave function, preserved unitarily forever. Black hole information paradox. Solved, information escapes in the Hawking radiation, scrambled but intact because unitarity, the core of many worlds, demands it. Let's now address a subtle but critical point. What is the ontology of the wave function? Is it real, like an electromagnetic field, or is it just a tool for calculating probabilities? In many worlds, it's real. The wave function is the fundamental entity. Particles, tables, stars, they're all emergent patterns in the wave function's evolution. This view, called wave function realism, treats configuration space, not three-dimensional space, as the arena of physics. A single particle lives in three-dimensional space. Two particles live in six-dimensional space, 3 for each. The universe lives in a space with 3 times the number of particles' dimensions. That sounds extravagant, until you realize that all interpretations of quantum mechanics use this high-dimensional space mathematically. Many worlds simply says, that's where reality lives. But there's an alternative, spacetime state realism, proposed by David Wallace and Chris Timpson. Here, the wave function isn't primary. Instead, quantum states are assigned directly to regions of spacetime, like assigning energy density or curvature in general relativity. This keeps physics grounded in 4-dimensional spacetime, avoiding the metaphysical weight of a high-dimensional space. Both views are compatible with many worlds. The debate is about how the wave function represents reality, not whether branching occurs. Now let's look at experimental frontiers. While we can't visit other branches, we can probe the limits of quantum coherence, the boundary where branching becomes irreversible. One cutting-edge experiment uses levitated optomechanics. A tiny glass sphere, hundreds of nanometers across, is held in place by laser light in ultra-high vacuum, cooled to near absolute zero. Researchers put it into a spatial superposition. The sphere is in two places at once, separated by more than its own diameter. They then watch as interactions with background gas or radiation cause decoherence, branching in real time. The rate of decoherence matches predictions based on environmental entanglement. No collapse, just smooth splitting. Another is the MAQRO proposal, a space mission to perform such experiments in orbit, where vacuum and microgravity reduce decoherence, allowing larger objects to be superposed. If a virus, or even a tardigrade, could be placed in superposition and show interference, it would powerfully demonstrate that quantum behavior isn't limited to the microscopic, and that branching applies to living systems. Then there's gravitational decoherence. Some theories, like Roger Penrose's, suggest gravity itself may cause collapse when mass distributions differ significantly between branches. Experiments with increasingly massive interferometers are testing this. So far, quantum behavior holds up to molecules of 25,000 atomic mass units. If it holds for even larger masses, collapse models lose ground. Many worlds gain support. Let's examine a famous objection, the preferred basis problem again. Why do we split into cat alive and cat dead, and not into cat alive plus cat dead and cat alive minus cat dead, some bizarre quantum mixture? The answer, as before, is decoherence. When the cat interacts with air molecules, photons, the box walls, the environment selects a basis, the pointer basis, in which information about the system is redundantly copied. This is called quantum Darwinism. Only states that can be broadcast to many parts of the environment survive as classical realities. Alive and dead are stable. Superpositions of them are fragile and rapidly decay into mixtures. Wojciech, who developed this idea, showed that the pointer basis is determined by the form of the interaction Hamiltonian, the part of the energy operator that couples system to environment. For position-coupled interactions like scattering, position is selected. For energy-coupled, like thermal contact, energy is selected. So the classical world emerges not by fiat, but by physics. Now let's derive, step by step in words, the Born rule from invariance as Yerk did. Suppose we have two systems, A and B, in a perfectly entangled state. Amplitude 1 over square root of 2 times the state where A is spin up and B is spin up, plus amplitude 1 over square root of 2 times the state where A is spin down and B is spin down. This state is invariant under a swap of A states if we simultaneously swap B states. That is, if we exchange up and down for A and also for B, the total state is unchanged. Now imagine preparing this state by first putting A in a superposition, then interacting it with B. An observer who only has access to A sees a mixed state, 50% up, 50% down. But because of the invariance, there's no physical difference between assigning probability 1/2 to up and 1/2 to down versus any other assignment, unless we demand that probabilities be invariant under invariant swaps. The only assignment that satisfies this symmetry is equal probabilities. Now generalize. Suppose the state is amplitude alpha times a up B up plus amplitude beta times a down B down, with alpha and beta complex numbers. By introducing an auxiliary system and performing invariant transformations, Yerk shows that the only probability assignment consistent with quantum symmetries is probability equal to the absolute value of alpha squared for up and absolute value of beta squared for down. Thus, the Born rule emerges, not as a postulate, but as a consequence of entanglement and symmetry. This is profound. It means that in a branching universe, rational agents must use the Born rule to guide their decisions. You don't choose to weight branches by squared amplitude. The structure of quantum correlations forces it upon you if you want your beliefs to be consistent with the physics. Let's now consider consciousness, not as a magical add-on, but as a physical process. Integrated Information Theory, or IIT, proposes that consciousness arises from the integrated information a system generates. Roughly, how much the system state specifies both its past and future, in a way that can't be reduced to parts. In a decoherent branch, a brain is highly integrated. Neurons fire in coordinated patterns, creating a unified experience. In a superposition of brain states, integration is low, because the system is entangled with the environment, not internally coherent. So consciousness only arises within branches, not across them. That's why you never experience being in two minds at once. This fits with clinical evidence. In split-brain patients, where the corpus callosum is severed, two separate streams of consciousness can emerge, each unaware of the other. Branching is like a natural, quantum version of that. The self splits when integration is lost due to decoherence. Now a practical question. Can we detect other branches indirectly? In 2014, a team led by Howard Weissman proposed the many interacting worlds model, not the same as many worlds, but inspired by it, where classical worlds repel each other, producing quantum effects. While controversial, it sparked experiments looking for anomalous forces between nearly identical systems. None found yet. More promising is weak measurement. In standard quantum mechanics, measuring a system disturbs it, but weak measurements, using very gentle probes, can extract average properties without full collapse. In 2011, researchers used weak measurement to reconstruct the average trajectories of photons in a double-slit experiment, and found they matched the Bohmian paths. But many worlds can also explain this. The weak value is an average over branches. So while not proof, it shows that hidden structures in the wave function have observable consequences. Let's talk about quantum computing once more, not as engineering, but as evidence for parallelism. A quantum computer with 300 qubits can represent 2 to the power of 300 states simultaneously. That's more than the number of atoms in the observable universe. When Shor's algorithm factors a large number, it doesn't try divisors one by one. It creates a superposition of all possible periods, then uses interference to amplify the correct one. If only one branch were real, this speedup would be inexplicable. But if all branches compute in parallel and interfere, it's natural. The fact that quantum computers work and scale as predicted is strong circumstantial evidence that the wave function's full structure is physically real. Now let's confront the emotional weight of this idea. Many people hear infinite versions of me and feel diminished. I'm not special. I'm just one thread in a tapestry. But consider, in a single universe view, you are an accident of chaos, a random fluctuation in a vast, indifferent cosmos. In many worlds, you are inevitable. Every choice you could make is made by a version of you who is just as real, just as worthy. Your struggles, your joys, your love, they all happen. Not once, but countless times, in variations that honor the full range of human possibility. This isn't nihilism, it's plenitude. The universe isn't stingy with existence, it's generous. And your role in it isn't to be the only hero in a lonely story, but to be a hero in this branch right now, making choices that ripple outward in love, in courage, in curiosity. Let's turn to philosophy, specifically the mind-body problem. How does subjective experience arise from physical processes? Many worlds doesn't solve this, but it reframes it. Instead of asking how matter produces mind, we ask, in which branches does mind arise? The answer, in those where the physical substrate brains or their equivalents achieve sufficient complexity and integration. Consciousness isn't added to physics. It's a phase of physics, like liquidity or superconductivity, emerging under the right conditions. And because branching is continuous, consciousness may not split discretely. Near the threshold of decoherence, there might be a brief period where integration is partial, leading to blurred or fragmented experience. Some meditative or psychedelic states might tap into this, sensing the edges of branching. This is speculative, but testable in principle with neural correlates of consciousness studies. Now a historical note. Hugh Everett didn't call it many worlds. He called it the relative state formulation. The name many worlds was coined by Bryce DeWitt in the 1970s, and Everett reportedly disliked it, fearing it sounded like science fiction. He saw it as pure quantum mechanics stripped of extras. Tragically, his work was ignored for over a decade. Discouraged, he left academia, worked in defense and computing, and died young. It wasn't until the 1980s, with the rise of decoherence theory, that his insight was vindicated. Today, polls of quantum foundations physicists show many worlds as the second most popular interpretation, after Copenhagen, but ahead of Bohmian and collapse models. Among quantum cosmologists and quantum information theorists, it's often the majority view. Why? Because it works, especially when there's no outside observer, like in the early universe. Let's do one last derivation of the uncertainty principle in words to see how branching respects limits. Suppose you prepare many identical particles, each in the same quantum state. You measure position on half of them, momentum on the other half. The standard deviation of the position measurements, call it delta x, times the standard deviation of the momentum measurements, delta p, is always greater than or equal to Planck's constant divided by 4 pi. Why? Because the wave function can't be sharply peaked in both position and momentum space simultaneously. A narrow wave packet in position requires many momentum components, like a short pulse of sound needing many frequencies. In branching terms, if you try to confine a particle to a tiny region, its momentum becomes highly uncertain, leading to rapid branching in momentum space. The more you pin down where it is, the faster where it's going splits into alternatives. This isn't a limitation of measurement, it's a feature of reality. And many worlds honors it. In each branch, position or momentum may be definite, but never both perfectly. Now let's imagine the far future, not heat death but rebirth. Some quantum gravity models suggest the universe could undergo a big bounce. After contraction, a new expansion begins. In many worlds, the wave function wouldn't collapse at the bounce. It would branch into histories with different bounce conditions. Some branches might preserve information from the previous cycle, others might not. We could be in a universe that's the latest in an infinite cycle, each iteration slightly different, exploring new possibilities. Or consider baby universes. Quantum fluctuations in spacetime could pinch off new, self-contained universes, connected by wormholes. In many worlds, these aren't separate spacetimes. They're new branches of the universal wave function, with their own decoherent histories. Stephen Hawking and Thomas Hertog recently proposed a top-down cosmology where the present selects the past, via the wave function's boundary conditions. Many worlds accommodates this. All pasts exist, but we only experience those consistent with our present. Let's return to you listening, perhaps now in that liminal space between wakefulness and sleep, where the subconscious is most receptive. I want to leave you with this. The many worlds interpretation isn't about escapism. It's not an invitation to imagine better versions of yourself elsewhere. It's a call to recognize that this version, you right now, with your aches and hopes, your unfinished work, is part of a grander reality that includes all possibilities, yet depends on this moment. Every time you choose patience over anger, curiosity over fear, connection over isolation, you're not just changing this world. You're strengthening a kind of branch, a lineage of worlds where compassion wins. The multiverse isn't a reason to despair, it's a reason to persist. Because somewhere in the vastness, a version of you did give up, and their world suffered for it. And somewhere else, a version of you kept going, and their world flourished. You get to decide which thread you follow. As we near the end of this journey, let's hear the Schrödinger equation one last time, not as a barrier, but as a lullaby of unity. The rate of change of the wave function with respect to time equals minus the square root of -1, multiplied by Planck's constant divided by 2 pi, multiplied by the inverse of the mass of the particle, multiplied by the sum over each spatial direction of the second derivative of the wave function with respect to that direction, plus the potential energy at that point multiplied by the wave function, all divided by Planck's constant divided by 2 pi, again multiplied by the square root of -1. This equation, this single line of physics, contains galaxies, cats, lovers, lullabies, and the quiet courage of a mind choosing to understand. It doesn't need collapse. It doesn't need observers. It just is, branching, ever branching into all that can be. And you are here not by chance but by necessity, a node in the network of existence, a witness, a participant. So as you drift towards sleep, know this: the universe is kinder, stranger, and more abundant than you've been told. And the physics, it's real. Thank you for listening.